James Webb just looked back to the beginning of time, and what it found shouldn't exist. Tonight, we're going to explore a discovery that quietly threw modern cosmology into crisis. For decades, we thought we understood how the universe grew up. It began in fire, then darkness, then slowly, over hundreds of millions of years, the first faint clumps of gas gathered in the black, and the earliest galaxies began to take shape. Small, dim, barely formed. We built a $10 billion telescope and flew it 1 million miles from Earth to look back and confirm that story. It saw something else. In its very first images of the early universe, the James Webb Space Telescope found galaxies that were too bright, too massive, too fully formed, structures that, according to every model we have, should not have had the time to exist. Some of them appear less than 300 million years after the Big Bang, already glowing with the light of hundreds of millions of stars. One of them has a spiral arm, a feature that's supposed to take billions of years to wind into place. They were not supposed to be there. By the end of tonight, you're going to understand exactly what James Webb saw in the first light of creation, why these galaxies break a timeline that scientists have trusted for half a century, and what it might mean if our entire story of how the cosmos assembled itself turns out to be wrong. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why these galaxies are such a problem, you first have to understand the story they break. And that story begins with the universe itself. Around 13.8 billion years ago, everything that exists was compressed into a state so hot and so dense that the words we use for space and time barely apply. Then it expanded. Not an explosion into space, but an expansion of space itself, in every direction at once. In the first fraction of a second, the universe ballooned from smaller than an atom to something vast. This is the Big Bang, and for a long time it was pure energy, too hot for atoms, too hot for light to travel freely. For about 380,000 years, the cosmos was an opaque fog, a glowing plasma of particles, so dense that light could not pass through it without slamming into something. Then the universe cooled. Electrons settled onto protons. The first atoms of hydrogen and helium formed. And suddenly, for the first time, light could move. That ancient flash is still arriving at our telescopes today, stretched and faded into the cosmic microwave background. It's the oldest light there is, the baby picture of everything, and then the lights went out. What followed is one of the strangest chapters in cosmic history. Astronomers call it the cosmic dark ages. There were no stars yet, no galaxies, just enormous silent clouds of hydrogen and helium drifting in an expanding darkness. The universe was there, but there was nothing in it that could shine. Imagine that for a moment. A cosmos the size of everything, completely dark, with no fire anywhere in it. That darkness lasted for somewhere between 100 and 200 million years. But the darkness was not empty. It was working. Because woven invisibly through all that gas was something we still don't fully understand. Dark matter. We can't see it. We can't touch it. But we know it's there because we can feel its gravity. And in the early universe, that dark matter was already pulling. Slowly, patiently, it gathered into vast invisible structures, a kind of cosmic scaffolding. And wherever the dark matter clumped most densely, ordinary gas flowed in behind it, drawn down into the gravitational wells. This is the heart of the story. This is how we believed galaxies were born. The model is called hierarchical assembly, and the idea is simple. You start small. Tiny pockets of gas collapse and ignite the first stars. Those first stars gather into small, ragged proto-galaxies. Then those small galaxies drift together and merge. Two become one. The one merges with another. Over hundreds of millions of years, then billions, the small things slowly build into big things. Little galaxies become medium galaxies. Medium galaxies become the grand spirals and giant ellipticals we see around us today. The key word in all of it is slowly. In this picture, you cannot rush a galaxy. A massive, mature galaxy is the end product of billions of years of merging and growing and forming stars. It's like a city. You don't find a sprawling metropolis a year after the first settlers arrive. You find a village. The city comes later, after generations of building. According to the standard model of cosmology, the same had to be true of the universe. The early cosmos should be a place of villages. Small, faint, disorganized, still under construction. For a long time, we had no way to test this directly because we simply couldn't see that far. And here's the beautiful thing about looking into deep space. When you look far away, you are also looking back in time. Light travels fast, but it does not travel instantly. It takes about 8 minutes for sunlight to reach your eyes, which means you never see the sun as it is, only as it was 8 minutes ago. Look at the next star over, and you're seeing light that left it years ago. Look at a distant galaxy, and you might be seeing light that's been traveling for billions of years. The telescope becomes a time machine. The deeper you look, the further into the past you see. So if you could just build a powerful enough eye and point it far enough out, you could in principle watch the early universe directly. You could see the villages being built. You could catch galaxies in the act of forming. For years, our best tool for this was the Hubble Space Telescope, and Hubble was extraordinary. It pushed back the frontier again and again, capturing galaxies whose light had traveled for more than 13 billion years. Its deepest images, the famous deep fields, revealed thousands of faint galaxies crowded into a patch of sky no bigger than a grain of sand held at arm's length. Hubble showed us the early universe was full of small, blue, irregular galaxies, exactly the villages we expected. The model was holding, but Hubble had a limit, and it was a limit of physics, not engineering. Because the universe is expanding, the light from the most distant galaxies gets stretched as it travels. The expansion of space literally pulls the light waves longer. Visible light, on its journey across 13 billion years, gets stretched out of the visible range entirely, shifted toward longer and longer wavelengths until it becomes infrared. We call this redshift. And the further away a galaxy is, the more its light is redshifted. Past a certain distance, the earliest galaxies stop glowing in the kind of light Hubble was built to see. Their light slides into the infrared, and to Hubble they simply vanish. To see past that wall, you needed a different kind of telescope, one built specifically to see in infrared, one cold enough and large enough to catch the faintest, most stretched-out light in the universe. And building it would become one of the most ambitious, most expensive, and most nerve-wracking projects in the history of science. That telescope is the James Webb Space Telescope. It carries a primary mirror 21 feet across, made of 18 gold-coated segments, far larger than anything Hubble could offer. To detect heat-faint infrared light from the dawn of time, the whole instrument has to be kept colder than almost anywhere in the natural universe, just a few degrees above absolute zero. To stay that cold, it can never feel the sun's warmth. So it flies 1,000,000 miles from Earth, far beyond the moon, with a tennis court-sized sunshield permanently angled to keep the sun, the Earth, and the moon all behind it at once. It does not look toward the light. It looks away from it, out into the dark, into the deep past. It launched on December 25, 2021. It spent 6 months unfolding, cooling, and aligning in the silence beyond the moon. And in July of 2022, It opened its eye on the universe for the first time and began sending back images. The plan was straightforward. Point the most powerful telescope ever built at the earliest moments we could reach. Find the villages. Watch the first small galaxies flicker into existence. Confirm the story we'd spent half a century refining. That is not what happened. Within weeks, the data coming back from those first deep images started to make astronomers uneasy. The galaxies were there, yes, right at the edge of time, exactly where we hoped to find them. But they were wrong. They were brighter than they should be. They held more stars than they should hold. They looked older, more settled, more built up than anything that early had any right to be. The villages we expected were not villages at all. We had sent an eye to the beginning of time to confirm what we knew. Instead, it found something that, by every rule we'd written, should not exist. Before we go any further, you need to understand the machine that found these galaxies. Because the strangeness of the discovery only makes sense once you grasp how this telescope sees and what it was built to do. The James Webb Space Telescope is not just a bigger Hubble. It is a different kind of eye entirely. Its primary mirror spans 21 feet across, made of 18 hexagonal segments that lock together into a single golden surface. Each segment is cut from beryllium, a light and rigid metal, then coated with a microscopically thin layer of pure gold. Gold, because gold is one of the best reflectors of infrared light that exists. The whole mirror gathers more than 6 times the light of Hubble. The fainter the object, the more this matters. And the first galaxies are the faintest objects we have ever tried to see. But size is only half of it. The real revolution is what kind of light Webb was built to catch. Hubble sees mostly the same light your eyes see, plus a little beyond. Webb was built to see infrared, heat light, light with wavelengths longer than the red end of what we can perceive. And this choice is not an accident. It is the entire point. Remember what happens to light as it crosses billions of years of expanding space. It gets stretched, redshifted. The visible glow of an ancient galaxy is pulled longer and longer until, by the time it reaches us, it has slid completely out of the visible range and into the infrared. To Hubble, that light is invisible. To Webb, it is exactly what it was designed to see. There's a second gift hidden in infrared: dust. The early universe is full of gas and dust, and visible light gets absorbed and scattered by it, blocked from view. But infrared light passes through dust far more easily. It slips between the grains. So Webb can see into places and back to times that were simply closed to us before. It sees the cold, the distant, and the hidden. To detect that faint heat light, though, the telescope itself has to be unimaginably cold. Here's the problem. Everything warm glows in infrared. You glow in infrared right now. A warm telescope would be blinded by its own heat, like trying to photograph a candle flame while staring into the sun. So Webb has to be colder than almost anywhere in the natural cosmos. Its mirrors and main instruments sit at around 40 degrees above absolute zero. That's roughly minus 370 degrees Fahrenheit. One of its instruments, the mid-infrared camera, has to be colder still, chilled by a dedicated cooler to just a few degrees above the absolute floor of temperature itself. Keeping anything that cold near the sun should be impossible, and this is where the design becomes genuinely beautiful. Webb carries a sunshield the size of a tennis court. 5 separate layers of a thin, shimmering material, each one thinner than a human hair, stretched out and held a small distance apart. The sun's heat hits the first layer, and most of it is reflected away. What gets through is radiated out the sides between the layers. By the time you pass all 5, the temperature has dropped by hundreds of degrees. One side of the shield faces the sun and bakes at over 200 degrees Fahrenheit. The other side, where the mirror lives, sits in a permanent deep freeze. The shield is always angled to keep the sun, the Earth, and the moon all behind it at once. And to make that possible, Webb does not orbit the Earth like Hubble does. It flies to a special point in space about 1 million miles away, 4 times farther than the moon. We call it the second Lagrange point, or L2. It's a gravitational sweet spot where the pull of the Earth and the Sun combine in a way that lets a spacecraft keep pace with our planet as we both circle the Sun. From out there, the Sun, Earth, and Moon all sit roughly in the same direction, which means one shield held at one angle can block all of them forever. Webb sits in that cold shadow, turned away from all the light, staring out into the dark. Now think about what that gives us. A giant golden mirror gathering ancient infrared light. An instrument cold enough to hear that light without drowning it out. A position far from the warmth and glare of home. Put it together, and you have a machine that can do something no human tool has ever done. It can look back past the wall where Hubble went blind. It can see the first few 100 million years after the Big Bang directly. And there's one more capability that turns Webb from a camera into a witness. It doesn't just take pictures. It takes spectra. It can split the light from a single galaxy into its component wavelengths, like a prism spreading sunlight into a rainbow. And hidden in that spread are sharp lines, fingerprints left by specific elements: hydrogen, oxygen, carbon. We know exactly what wavelengths those fingerprints sit at when the light is fresh. So when we see them shifted far toward the red, we can measure precisely how much the light has been stretched. And that tells us with hard certainty how far the light has traveled and how far back in time we are looking. A photograph can fool you. A spectrum cannot. This is how Webb doesn't just spot a distant galaxy. It proves how distant it is. Imagine, for a moment, what it means to point this eye at a blank patch of sky and hold it there. Photons that left a galaxy more than 13 billion years ago, that have been traveling across an expanding universe for almost the entire history of everything, finally end their journey on a gold-coated mirror 1 million miles from the planet where, eventually, the curious creatures who built that mirror would evolve. You are not looking at a picture of the past. You are catching the actual ancient light, the very same particles, arriving right now. In the summer of 2022, after 30 years of work and a million-mile journey, that is exactly what astronomers prepared to do. They chose their patches of sky. They opened the shutter, and they waited to see the dawn of the universe with their own instruments for the first time. On July 11, 2022, the first full-color image from the James Webb Space Telescope was revealed to the world. It was a single, deep view of a tiny patch of sky, a region called SMACS 723, and it was breathtaking. Thousands of galaxies scattered across the black, in a field of view so small you could cover it with a grain of sand held at arm's length. Some of those galaxies were among the most distant ever captured. The light had been traveling for billions of years. There was an extra trick at work in that first image. In the foreground sat a massive cluster of galaxies, and its enormous gravity bent the space around it, acting like a giant lens. Light from even more distant galaxies behind the cluster was warped and magnified as it passed, smeared into arcs and curves. Astronomers call this gravitational lensing, and it let Webb peer even deeper, using the cluster itself as a natural magnifying glass. Galaxies that would otherwise be too faint to detect were lifted into view. The public saw a beautiful picture. Astronomers saw something else. They saw targets. And within days, telescope time across several major survey programs began pouring out data from the early universe. Programs with names like CEERS and GLASS and JADES, each one staring into selected patches of darkness, each one reaching for the faintest, reddest, most distant smudges they could find. The plan, remember, was to find the villages, the small, faint, primitive proto-galaxies that the standard model said should populate the early cosmos. And the galaxies were there, right at the edge of reach, exactly where they were expected to be. But almost immediately, something about them felt wrong. They were too bright. In those first weeks, paper after paper appeared, posted by teams racing to analyze the new data. Candidate galaxies at staggering distances, objects whose light appeared to come from just 300 or 400 million years after the Big Bang. And there were more of them than there should be, and they shone more brightly than they should. The early universe in Webb's first glance did not look dim and sparse and under construction. It looked surprisingly bright, surprisingly full, surprisingly far along. To understand why this rattled people, you have to understand how these first distances were measured. In the rush of those early weeks, most of the distances were what astronomers call photometric redshifts. The idea is this. Webb photographs each patch of sky through a series of filters, each one capturing a different band of infrared light. A very distant galaxy has a telltale signature. Below a certain wavelength, its light is almost completely absorbed by the hydrogen gas between us and it, so it abruptly drops out of the shorter filters and appears only in the longer ones. By measuring which filters a galaxy shows up in and which it disappears from, you can estimate how much its light has been stretched, and therefore roughly how far away it is. It's clever and it's fast, but it's an estimate, and there's a danger built into it. A genuinely ancient, distant galaxy and a much closer galaxy full of red dust can, in certain cases, produce a similar pattern across the filters. A nearby imposter can masquerade as a cosmic record breaker. So the early candidates came with a warning label. These were strong leads, not confirmed facts. To know for sure, you needed a spectrum. You needed to split the light and read the fingerprints directly. And so attention settled over the field. On one side, image after image suggesting an early universe that was far too bright, far too built up, far too soon. On the other side, the sober caution of scientists who had seen exciting candidates evaporate before. Maybe some of these galaxies weren't as far away as they looked. Maybe the models for how to interpret the filters needed adjusting. Maybe, when the spectra came in, the problem would soften and the villages would reappear. But the unease would not go away, because it wasn't just one or two odd galaxies. It was a pattern, showing up across different surveys in different patches of sky, analyzed by different teams. The early universe kept coming back brighter than the theory allowed. And the deeper question, the one that started to keep cosmologists up at night, was not about any single galaxy. It was about what it would mean if the pattern held. Because if these galaxies really were that far away and really were that bright, then the light wasn't the problem. The light was just light. The problem was what the light implied. To shine that brightly, that early, a galaxy needs stars, a great many stars. Which means a great deal of matter had to be gathered, and collapsed, and ignited, in far less time than the standard story said was possible. Brightness in the end is a clue to mass, and mass in the early universe is a clue to time. The question Webb had quietly raised in its very first images was the most dangerous question in cosmology. How did so much get built so fast? To answer that, the field needed harder numbers. Not estimates from filters, but masses, measured and weighed. And when those numbers started to come in early 2023, the unease became something closer to alarm. In February of 2023, a team of astronomers published a result that made headlines around the world. Using Webb's data, they had identified 6 galaxies in the early universe, seen as they were roughly 500 to 700 million years after the Big Bang. And when they estimated the masses of these galaxies, the numbers were staggering. Some of them appeared to contain as much mass in stars as the Milky Way does today. Tens of billions, in some cases approaching 100 billion times the mass of our Sun, in stars, already, when the universe was less than 5% of its current age. The press called them universe breakers. The name stuck because it captured the feeling exactly. According to the standard model of how galaxies form, these objects should not have been able to exist. Not yet. Not for billions of years. To feel the weight of that, return to the story of how galaxies are supposed to grow. Hierarchical assembly. You start with small clumps of gas drawn together by the gravity of dark matter. Stars ignite, small galaxies form, and then slowly, over enormous spans of time, these small galaxies merge and accumulate and build themselves up into the giants we see around us. It is a process measured in billions of years. A massive galaxy is supposed to be an old galaxy. The end of a long road, not the beginning. There's a second, harder limit underneath this, and it has to do with raw bookkeeping. In any region of the early universe, there is only so much ordinary matter available. Hydrogen and helium gas, pulled into the gravitational wells carved out by dark matter. You can calculate from the standard model roughly how much of that gas should exist in a given volume at a given time. And here is the brutal part. Even if a galaxy took every single atom of available gas and converted all of it into stars with perfect total efficiency, in some cases it still could barely account for the masses being reported. There would be almost nothing left over. That should set off alarms because galaxies are not efficient. Real galaxies are messy and wasteful. Star formation blows gas back out into space. Radiation pushes it away. Exploding stars scatter it. In a normal galaxy, only a small fraction of the available gas, often just a few percent, ever actually becomes stars. The rest is lost, heated, or blown clear. So to build a galaxy as massive as the Milky Way just a few 100 million years after the Big Bang, you would need star formation running at an efficiency far beyond anything we observe in the modern universe. You would need the early cosmos to be converting nearly all of its gas into stars, almost without waste. And nothing in our models said it could do that. So there were really only a handful of possibilities, and each one was uncomfortable. Either the masses were wrong, and these galaxies were less massive than they appeared, or the distances were wrong, and they were closer than they looked. Or star formation in the early universe was wildly more efficient than anywhere we'd ever seen. Or, in the most radical case, something in our understanding of the early universe itself, the amount of matter, the behavior of dark matter, the timeline of structure formation, was missing a piece. Now, science is conservative, and it should be. The most exciting explanation is almost never the first one you accept, and there were good reasons for caution here. Estimating a galaxy's mass from its light is genuinely difficult. The amount of light a galaxy gives off depends not just on how many stars it has, but on what kind. A galaxy can look extremely bright either because it is enormously massive, or because it is forging a smaller number of unusually massive, brilliant stars in a sudden, furious burst. Those two scenarios can produce similar brightness with very different masses. There was also the lingering question from the photometric distances. If even some of these galaxies were closer imposters, their estimated masses would shrink dramatically. In the months that followed, this is exactly what scientists set out to test. Webb turned its spectrograph on the candidates, one by one, to pin down their true distances and read the chemistry of their light. And the results were a genuine mix. Some of the extreme early candidates did turn out to be lower redshift interlopers, nearby galaxies in disguise, exactly as the skeptics had warned. The problem in those cases dissolved, but many others held. Their distances were confirmed. Their brightness was real. And while careful spectroscopy often trimmed the mass estimates down from the most extreme early headlines, it did not make the puzzle disappear. It left behind a hard residue of galaxies that were still, by the standards of the old model, too luminous and too developed for their age. This is the thing to hold on to. The universe breakers were not a single dramatic mistake that got corrected. They were the loud first signal of a quieter, more durable problem. Even after the dust settled, after the imposters were removed, and the masses were refined, the early universe that Webb revealed was simply more vigorous than our theories predicted. There were too many bright galaxies too early. The cosmic dawn was busier than it had any right to be, and the deeper Webb looked, the worse it got. Because the galaxies we have talked about so far, at 500 or 600 million years, were not even the edge of what Webb could reach. The telescope was about to push further still, to galaxies seen less than 300 million years after the beginning, to the very frontier of the observable past. And what it found there would set records that, just a few years earlier, most astronomers would have said were impossible. To talk about the most distant galaxies, we need to talk about redshift again, but in a more precise way. Because redshift is the number astronomers actually use to describe how far back in time they are looking. It is written with the letter Z. The larger the Z, the more the light has been stretched, the farther away the galaxy is, and the earlier in cosmic history we are seeing it. To give you a feel for the scale, a redshift of 1 takes you back roughly 8 billion years. A redshift of 6 lands you around the first billion years of the universe. A redshift of 10 brings you to about 470 million years after the Big Bang. For a long time, redshift 10 was the frontier, the edge of the reachable. The Hubble Space Telescope, after years of effort, managed to find a single remarkable galaxy at a redshift of around 11, called GNZ 11, seen as it was about 430 million years after the beginning. It was the distance record holder, and it sat alone at the edge of what we could see. Many astronomers expected it to hold that record for a long time. Webb shattered that frontier almost immediately. When Webb later turned its spectrograph on GNZ 11, it confirmed the galaxy's extreme distance and revealed it to be even stranger than thought, startlingly bright and compact, with hints of an extraordinarily dense cluster of stars and possibly a feeding black hole at its core. The old record holder turned out to be not a quiet little proto-galaxy, but an intense, luminous engine. And that was just the beginning. Survey after survey began turning up candidates beyond redshift 10, then beyond 12, each one pushing closer to the absolute edge of the observable universe, to the moment when there simply were no galaxies yet, only darkness and gathering gas. And then came the one that, as of now, stands at the very frontier of confirmed distance. A galaxy catalogued as JADES GSZ 140. Its redshift was measured through spectroscopy at 14.32. Let that number settle. A redshift of more than 14. The light from this galaxy left it when the universe was only about 290 million years old. Barely 2% of its current age. We are seeing it as it was almost 13.5 billion years ago, in the deep cosmic dawn, when the first generations of stars were still new. And once again, the galaxy refused to be small and faint. It was luminous, far brighter than models suggested anything that early should be. It was also surprisingly large, stretching across something like 1,600 light-years, and clearly built from the light of many millions of stars. Its spectrum even showed signs of oxygen, and that detail carries a strange weight because oxygen does not exist on its own at the beginning of the universe. The Big Bang made only hydrogen, helium, and a whisper of lithium. Every oxygen atom in existence had to be forged in the core of a star and then scattered out when that star died. So finding oxygen this early means that an entire prior generation of stars had already lived, fused heavier elements in their cores, and exploded, seeding the gas, all before the moment we are looking at. There was already a chapter of cosmic history behind this galaxy, at a time we used to think of as the very first page. This is what makes redshift 14 so vertiginous. It is not just a far-off smudge. It is a fully lit, chemically enriched galaxy, existing at a moment when, by the slow logic of hierarchical assembly, the universe should still have been mostly assembling its very first stars. And crucially, this distance is not an estimate from filters. It was confirmed by reading the stretched fingerprints in the galaxy's actual spectrum. There is no imposter hiding here. The distance is as solid as these measurements get. Now, take a step back and stack what Webb has shown us so far. At 5 and 600 million years, galaxies that are too massive and too bright. At 400 million years, luminous engines where we expected dim beginnings. At under 300 million years, a galaxy already enriched with the ashes of a previous stellar generation. The pattern doesn't break as you go earlier. It sharpens. Every time Webb reaches closer to the beginning, it finds the universe further along than the theory says it should be. And yet, for all their strangeness, these record-breaking galaxies point to a question we have so far walked right past. That galaxy at redshift 14 already held oxygen, and oxygen has to be forged inside a star and scattered by its death, which means some earlier star had already lived and died before this galaxy ever shone. So to understand the cosmic dawn, we cannot begin with these galaxies. We have to go back further still, to the generation that came before them, to the very first stars that ever burned. And they may be the strangest objects the universe has ever made. We have never seen one, not directly, but we can reason our way toward what they must have been like, and the picture is staggering. Go back to the very first gas before any star existed. It was almost pure simplicity, about 3/4 hydrogen, 1/4 helium, and essentially nothing else. No carbon, no oxygen, no iron. Astronomers have a slightly confusing habit of calling every element heavier than helium a metal, and by that definition, the early universe was completely metal-free. And that one fact changes everything about how the first stars could form. Here's why. To build a star, a cloud of gas has to collapse under its own gravity, and to collapse, it has to cool. As gas falls inward, it heats up, and that heat pushes back, resisting the collapse. Something has to bleed the heat away. In the universe today, heavier elements are extraordinarily good at this. They radiate heat efficiently, letting gas cool and break into many small clumps, which is why most stars that form today are modest, like our Sun, or smaller. But the first gas had none of those elements. It could barely cool at all. So instead of fragmenting into many small stars, the primordial cloud stayed hot and collapsed as enormous single units. The result was a kind of star the universe has perhaps never made since. The first stars, the ones astronomers call Population 3, are thought to have been monsters, not a little larger than the Sun, tens, possibly hundreds of times its mass. Giants of pristine gas, blazing into existence in the dark. And a star like that does not live a gentle life. The more massive a star, the hotter it burns and the faster it consumes itself. Our Sun will shine for roughly 10 billion years. These first giants would have burned through their fuel in just a few million. They lived fast, blindingly bright, pouring fierce ultraviolet light into a universe that had known nothing but darkness for 100 million years. They were the first light. The end of the cosmic dark ages began with them. Then they died, and they died spectacularly. The most massive of them are thought to have ended in an explosion so violent it has a special name, a parent stability supernova, in which the star is not merely blown apart but completely obliterated, leaving nothing behind at all. No core, no remnant, just an expanding cloud of newly forged elements, the first oxygen, the first carbon, the first iron, flung out into space. Everything that would later become planets and oceans and stone and bone was first cooked inside these stars and scattered by their deaths. So the first stars are not just an astronomical curiosity. They are the origin of the material world, the bridge between a cosmos of pure hydrogen and a cosmos that could one day build worlds. And that is exactly why finding them is one of the great prizes of modern astronomy. The trouble is, they are almost impossibly hard to see. They existed so early and burned for such a short time that catching one is like trying to photograph a single match struck and snuffed out on the far side of a stadium billions of years ago. For a long time, it seemed they might be forever beyond reach, but Webb has given us a real chance, for the first time. Astronomers are hunting for the telltale fingerprints of these first stars, a galaxy glowing with the signature of helium but showing no trace of heavier elements. A burst of light with exactly the wrong colors to be ordinary stars. And there have already been tantalizing hints, candidate pockets of pristine, metal-free gas glimpsed in the deep field, suggestive but not yet confirmed. We have not caught a first star in the act. Not yet. But we are closer than we have ever been, and Webb may yet be the telescope that does it. And here is the twist that fits everything else we have seen. The early universe keeps refusing to be primitive. Even the hunt for the first, simplest stars keeps bumping into the same surprise. By the time Webb looks, the gas has so often already been enriched, already seeded with the ashes of an earlier generation, that the truly pristine first stars keep slipping just out of frame, always a little earlier than we can quite reach. The cosmic dawn was busier and faster than we ever expected all the way down. But the first stars were not the only thing hiding in that early light. Webb also found objects that were not faint and primitive at all. They were tiny, brilliant, and a deep, saturated red, and there were far too many of them. When astronomers first started combing through Webb's deep images, they kept noticing a peculiar kind of object, not a sprawling galaxy, not a faint smudge, something small, almost point-like, and a deep, saturated red. Then they noticed another, and another. Soon it was clear these things were everywhere in the early universe, far more common than anyone expected. They needed a name, and the one that stuck was disarmingly simple: the little red dots. At first glance, a little red dot doesn't look like much, but the more closely astronomers studied them, the stranger they became. They are extremely compact, far smaller than a normal galaxy, with their light concentrated into a tiny central point. They are intensely red, and there are a lot of them, scattered across the cosmic dawn in numbers that don't fit easily into any existing picture. So the obvious question became, what are they? There are two main answers, and both lead somewhere uncomfortable. The first possibility is that a little red dot is a galaxy forging stars at a furious rate, wrapped in so much dust that its light is reddened and dimmed as it escapes, the way the setting sun turns red as its light pushes through thick atmosphere. That would be strange enough on its own, because it would mean dense, dusty, star-choked galaxies had assembled remarkably early. But the second possibility is the one that really unsettles people. A little red dot might not be glowing with starlight at all. It might be glowing with the light of matter falling into a supermassive black hole. When gas spirals down toward a black hole, it doesn't fall silently. It piles up into a searing, swirling disk, heated by friction and compression until it blazes brighter than entire galaxies. We call these objects active galactic nuclei, and the brightest of them, quasars, are among the most luminous things in the universe. And when Webb took spectra of many little red dots, it found a signature consistent with exactly this. Gas moving at enormous speeds, the kind of motion you'd expect from material whipping around a massive black hole, which suggests that a huge number of these tiny red objects in the early universe are not just galaxies. They are early black holes, already feeding, already massive. And that opens a door onto one of the deepest mysteries Webb has deepened. The problem of how supermassive black holes got so big, so fast. Even before Webb, this was a puzzle. Astronomers had found fully grown quasars, powered by black holes weighing 1 billion times the mass of our Sun, existing less than 1 billion years after the Big Bang. A billion-sun black hole is already a monster. The one at the center of our own galaxy is only about 4 million solar masses. So how do you build something 1,000 times heavier than that, in less time than it took the rest of the universe to make its first galaxies? Here's why that's hard. There is a natural speed limit on how fast a black hole can grow. As it pulls in matter, that matter heats up and radiates, and the radiation pushes outward, shoving away the very gas the black hole is trying to swallow. Past a certain rate, the outward push of light balances the inward pull of gravity, and the black hole effectively chokes on its own brilliance. This ceiling is called the Eddington limit, and if a black hole grows at that maximum steady rate, starting from a seed left behind by an exploding star, the math simply does not allow it to reach 1 billion solar masses in the time available. It would still be far too small. Webb made this worse, not better. By revealing black holes that appear surprisingly massive at surprisingly early times, it sharpened the question rather than answering it. One object, seen as the universe was around 570 million years old, appears to host a black hole of roughly 10 million solar masses, already enormous for its age. Another, even further back, near a redshift of 10, was detected glowing in X-rays by a separate telescope, and it seems to contain a black hole so heavy that it rivals the entire mass of stars in its host galaxy. In the modern universe, a central black hole is typically a tiny fraction of its galaxy's mass. Here, the black hole and the galaxy look almost matched, as if in some cases the black hole came first and the galaxy grew up around it. So how do you solve it? Astronomers have a few ideas, and they are all dramatic. Maybe these early black holes broke the speed limit, feeding in short, violent bursts far above the Eddington rate, gorging faster than the radiation could stop them. Or maybe they didn't start from the corpse of a single star at all. Maybe, in certain an enormous cloud of gas collapsed directly into a black hole in one catastrophic step, skipping the stellar stage entirely and beginning life as a heavy seed, tens of thousands of solar masses, with a massive head start. We call these hypothetical objects direct collapse black holes, and the little red dots may be our first real glimpse of them in action. Imagine standing at the edge of one of these early galaxies looking inward. You would not see a calm spiral. You would see a small, blindingly bright core, an infant black hole already as heavy as millions of suns, dragging in torrents of gas, blazing in the dark, growing at a pace that our equations say should not be possible. The cosmic dawn in this light was not a gentle awakening. It was violent and it was fast, and at its heart sat engines we are only beginning to understand. And just when it seemed the early universe could not surprise us in any new way, Webb found something that broke a different rule entirely. Not too massive, not too bright, too organized. In early 2025, astronomers announced the discovery of a galaxy they nicknamed the Big Wheel, and the reason it made news was not its mass or its brightness. It was its shape. The Big Wheel is a spiral galaxy, a great, sweeping disk of stars wound into graceful arms, not unlike our own Milky Way. And it existed when the universe was only about 2 billion years old. To make matters stranger, it is enormous, one of the largest disk galaxies known from that era, far bigger than models would predict for its time. A massive, beautifully ordered spiral fully formed in the young universe. To understand why a spiral is such a problem, you have to understand what a spiral actually is. A grand spiral galaxy is not a chaotic blob. It is a finely tuned, rotating disk, where billions of stars all orbit in roughly the same plane, in roughly the same direction, in calm, settled motion. That kind of order does not come easily. It is the opposite of how the early universe behaves. The cosmic dawn in our models is a violent place. Galaxies grow by colliding and merging, by swallowing streams of gas falling in from all directions. All of that crashing and feeding stirs the gas into turbulence, like a pot at a rolling boil. Stars form out of that chaos in clumpy, irregular shapes. To become a smooth, rotating spiral, a galaxy has to do something difficult. It has to settle. The mergers have to slow down. The turbulence has to calm. The gas has to cool and organize itself into a thin, orderly disk that can rotate in peace. And settling like that is supposed to take a long time. Billions of years. Grand spirals in the standard picture are a feature of the mature, middle-aged universe, not its turbulent youth. So a fully wound spiral, this large, this early, is yet another thing that should not be there. Yet another sign that the early universe organized itself faster than the theory allows. But here is where we need to be careful and honest, because this is exactly the kind of place where the story can run ahead of the science. The Big Wheel is a striking object, but it is one object. And there is a trap in studying the early universe called selection. The galaxies that are easiest to find at extreme distances are the brightest, the biggest, the most dramatic ones. The faint, ordinary, expected galaxies are far harder to see. So if you only look at the giants that grab headlines, you can fool yourself into thinking the whole early universe was full of giants, when really you are just seeing the rare extremes, the cosmic outliers, while the unremarkable majority stays hidden in the noise. And in fact, when astronomers did the harder work in late 2025 of studying not just the spectacular giants but hundreds of smaller, more typical early galaxies, a more reassuring picture emerged. Looking at the motion of gas inside this broader population, they found exactly what the old models predicted. Most early galaxies were messy, turbulent, disorganized, struggling to settle. They had not yet calmed into orderly disks. The graceful, well-behaved spirals were the exception, not the rule. As one of the researchers put it, when you stop fixating on a few showpieces and look at the bigger sample, the early universe falls much more in line with theory. So which is it? Is the early universe shockingly organized or reassuringly messy? The honest answer, the scientific answer, is that this is exactly what an open question looks like while it is being resolved. The giants are real, and they are genuinely hard to explain, but they may be rare exceptions rather than the norm. The puzzle is not that every early galaxy is impossible. The puzzle is that some of them are, and that even a handful of impossible galaxies is enough to tell us our models are missing something. This is the texture of real science. Not a single clean shock, but a tug-of-war between the spectacular and the ordinary, fought one spectrum at a time. And it is exactly because the stakes are so high that the field is being so careful. Because if even the most conservative explanations fail, The alternative is to start questioning some of the deepest assumptions we hold about how the universe is built. But the impossible galaxies and their blazing cores did more than just confuse our models. All of that early light had a consequence on the grandest scale imaginable. It did not merely reveal the early universe to us. It transformed the early universe itself. It reached out into the surrounding darkness, and it ended it. To see how, we have to return to the darkness those first galaxies were born into. Remember the cosmic dark ages. After the universe cooled enough to form the first atoms, it became a vast ocean of neutral hydrogen gas. Neutral, meaning each hydrogen atom held onto its electron. And neutral hydrogen has a peculiar property. It behaves like a fog. It absorbs certain kinds of light, especially the ultraviolet light that young, hot stars pour out. So even once the first stars ignited, their most energetic light could not travel far. It was swallowed by the surrounding gas. The universe was, in a sense, still opaque to its own first fires. Then slowly, the fires began to win. The intense ultraviolet radiation from the first stars and galaxies started tearing electrons off the surrounding hydrogen atoms, a process called ionization. Around each early galaxy, a bubble formed, a region where the hydrogen had been stripped bare, ionized, and made transparent. Inside the bubble, light could finally travel freely. And as more and more stars lit up across the cosmos, these bubbles grew. They expanded outward into the surrounding fog. They began to overlap. They merged with their neighbors, bubble joining bubble, transparency spreading like dawn breaking across a foggy valley. This great transition has a name, the epoch of reionization. It is the moment the universe went from opaque to clear, from a dark fog to the transparent cosmos we live in today. And it was not a single event but a gradual sweep, beginning a few 100 million years after the Big Bang and completing, by most measures, around 1 billion years in. After it was over, the fog was gone for good. Light could cross the universe freely, and it has ever since. Now here is where this connects directly to Webb's most puzzling discovery. For decades, astronomers have wrestled with a simple question about reionization. What did it? What produced enough ultraviolet light to ionize all the hydrogen in the entire universe? The leading suspect was always the early galaxies, but there was a nagging doubt. Were there really enough of them? Did they shine brightly enough? And did enough of their ultraviolet light actually escape into space rather than being trapped inside them to get the job done? And remember what Webb found. Too many galaxies, too bright, earlier than expected. The very same surprise that caused the impossible galaxy crisis may, in this corner of the story, turn out to be the answer to a different mystery. If the early universe really was more crowded with bright galaxies than we thought, then perhaps the puzzle of reionization eases. Perhaps there were enough sources after all, blazing in the cosmic dawn, to burn away the fog. One discovery's problem may quietly become another's solution. Webb is now mapping this transition directly. By looking at galaxies at different distances and measuring how much of their light is absorbed by the hydrogen around them, astronomers can chart how neutral or how ionized the universe was at each moment. They are watching the fog lift, age by age, reconstructing the exact timeline of when the lights came on. It is one of the most important things the telescope is doing, because reionization is the hinge between the dark, formless early universe and the structured, transparent cosmos that everything else, including us, would grow up in. So step back and see the shape of it. The first stars ignited in darkness. Their galaxies gathered and blazed. Their combined light reached out and ionized the universe, clearing the fog, ending the dark ages, and making the cosmos transparent to its own light forever after. It is, quite literally, the story of how the universe learned to shine. And none of it, not the first stars, not the impossible galaxies, not the timeline of reionization, would be known to us at all if we had not first done something almost as improbable as the cosmic dawn itself. We had to build the eye that could see it, a machine cold enough, and large enough and far enough from home to catch light from the beginning of time. And the story of how we built that machine, of how close it came to never existing, is its own kind of impossible. Here is something worth sitting with. Every discovery we have talked about, every impossible galaxy, every blazing little red dot, every record at the edge of time, exists only because thousands of people spent decades building a machine that, by all rights, should have been too hard to build. The idea for a successor to Hubble was born before Hubble had even proven itself, back in the late 1980s and refined through the 1990s, under the plain name the Next Generation Space Telescope. The concept was audacious from the start. To see the first galaxies, you'd need a telescope far larger than Hubble, cooled to near absolute zero, parked a million miles from Earth. Each of those requirements was, on its own, a monumental engineering challenge. Together, they bordered on the absurd. Start with the mirror. To gather enough ancient light, Webb needed a mirror over 21 feet across. But no rocket has a nose cone wide enough to hold a mirror that size. So the engineers made a decision that sounds almost reckless. They would build the mirror in 18 separate hexagonal segments, folded up like a piece of origami, fitted inside the rocket, and then unfolded in space, with each segment aligning to within a fraction of the width of a human hair. A mirror that assembles itself, a million miles away, where no human hand could ever fix it. Then the sunshield. 5 gossamer-thin layers, each the size of a tennis court, folded into a package small enough to launch, then stretched taut in space by a system of motors, cables, and booms. Hundreds of mechanisms had to fire in the right order. Membranes thinner than a hair had to unfurl without tearing, without snagging, without sticking together. And if any one step failed, the telescope would never get cold enough to see, and the whole mission would be lost. This is the part that made everyone who understood it lose sleep. When engineers tallied up the deployment, they counted hundreds of individual steps that simply had to work, each one a potential point of failure with no backup and no second chance. Unfolding the mirror. Releasing the segments. Extending the booms. Separating and tensioning each of the 5 shield layers. A long chain of single points of failure where one stuck pin or one jammed motor could end everything. And unlike Hubble, which astronauts had famously flown up to repair when its vision came out blurry, Webb would be 4 times farther away than the moon. No astronaut could ever reach it. Whatever happened out there happened alone. And all of this came at a staggering cost, and after years of painful delay. The project ran far over its original budget and far past its original timelines, eventually reaching a price tag around $10 billion. There were redesigns, technical setbacks, and schedule slips measured in years. At one point in 2011, the United States Congress came within a hair of canceling the entire program, ready to walk away from a decade of work and billions already spent. It survived by the narrowest of margins, kept alive by people who believed that what it could show us was worth the gamble. Imagine being one of those engineers. You have given 15, 20, in some cases 30 years of your career to this single machine. You have watched it nearly die in budget battles. You have run every test you can think of on the ground, knowing the one environment you can never fully simulate is the one place it actually has to work. And now you are about to fold it up, seal it inside a rocket, and fire it a million miles into the dark, where it will have to perform hundreds of flawless mechanical miracles in a row, completely beyond your reach. On December 25, 2021, after years of waiting, the James Webb Space Telescope lifted off atop a rocket from the coast of South America and rose into the sky. The launch was only the beginning. What followed was a stretch of time the team spoke about with open dread. Day after day, as the telescope coasted toward its distant post, the deployments began. The sunshield unfolded, layer by agonizing layer. The mirror wings swung into place. The segments locked. Each step was monitored from the ground, with the awful knowledge that no one could intervene if something went wrong. And one by one, against the fears of nearly everyone who understood the odds, the steps worked. The shield tensioned. The mirror unfolded and aligned. The telescope reached its post a million miles out, settled into the cold shadow, and began to cool toward the deep freeze it needed to see. Months of careful commissioning followed, focusing the mirror, calibrating the instruments. And then, in the summer of 2022, the most ambitious telescope ever built opened its eye on the universe, and the impossible machine began returning the impossible galaxies. So when we talk about a galaxy at the edge of time, remember what stands behind that image. Not just 13 billion years of traveling light, but 30 years of human stubbornness. A mirror that folded itself open in the dark. A gamble that very nearly didn't happen. We almost didn't build the eye. And if we hadn't, we would still believe the early universe was exactly what our models said. Quiet, slow, simple. We would never have known how wrong we were, but we did build it. And now that we have seen what it shows us, we are left with the hardest question of all. What does it mean? Are these galaxies a puzzle our existing theories can still solve with enough cleverness and enough new data? Or are they the first cracks in the foundation, the first hint that something in our deepest understanding of the universe is simply wrong? When nature hands scientists something that shouldn't exist, the response is not panic. It's a long, stubborn search for an explanation that fits, and in the case of the impossible early galaxies, that search is well underway. There are several serious ideas on the table. Most of them do not require throwing out physics. They require something subtler. They require us to have misjudged how the early universe made its light. The first idea is about timing and trickery. Galaxies don't form stars at a steady pace. They do it in bursts. A galaxy can sit quiet, then suddenly ignite a furious wave of star formation, blazing brightly for a brief moment before settling down again. Now consider what that does to a survey. If galaxies flicker, then at any given time, the ones we notice are disproportionately the ones caught mid-flare, shining far above their normal brightness. We see the universe at its brightest moments and mistake those flashes for the steady state. The galaxies look more luminous, and therefore more massive than they typically are. This effect, where a burst makes a modest galaxy briefly impersonate a giant, may account for a real chunk of the excess. The second idea is stranger, and it concerns the stars themselves. When we estimate a galaxy's mass from its light, we have to assume something about what kinds of stars are producing that light. We assume a certain mix, mostly small, dim stars with a sprinkling of large, bright ones, the proportions we see in the universe today. But what if the first stars were different? What if in the early universe, with its pristine gas and harsher conditions, nature favored larger, hotter, more brilliant stars? A small number of massive stars can outshine a vast crowd of small ones. So if early galaxies were top-heavy, weighted toward giants, then they could produce all that light with far less total mass than we assumed. The brightness would be real. The enormous mass would be an illusion, an artifact of assuming the wrong kind of stars. The third idea is about efficiency. Recall that normal galaxies are wasteful, converting only a few % of their gas into stars before feedback blows the rest away. But what if the earliest galaxies were better at it? In the dense, compact conditions of the cosmic dawn, gas was packed more tightly, and the usual mechanisms that disperse it may have been weaker or slower to kick in. If early galaxies could convert a much larger fraction of their gas into stars before losing it, they could build up mass faster than the standard recipe allows, without breaking any law, just by being more efficient than their descendants. A fourth idea takes aim at the dust. Some of the early galaxies look too mature partly because of how much dust they seem to contain, and dust is supposed to come from old, dying stars. But dust that is warmer shines more brightly than the same amount of cooler dust. Observations of certain early galaxies suggest the dust there really is hotter than expected. If so, then a small amount of warm dust can mimic the glow of a large amount of cool dust, and you no longer need a huge population of ancient stars to explain it. The galaxy looks older than it is. And then there is the black hole question. We saw that many of the little red dots may be feeding black holes rather than pure starlight. That matters here too, because if some of the light we attributed to stars is actually coming from gas falling into a black hole, then we have been overcounting the stars. Strip out the black hole's contribution, and the stellar mass shrinks. Several of the most extreme early objects may be less stuffed with stars than they first appeared, with a hidden engine doing some of the shining. Put these together and a reassuring picture starts to form. Bursting star formation, top-heavy stars, higher efficiency, warmer dust, hidden black holes. None of them rewrites physics. Each chips away at the problem. And when astronomers replaced the early estimates with careful spectra, removing the imposters and refining the masses, the most outrageous claims did soften. The universe breakers got smaller. The crisis cooled. And this is the crucial but it did not vanish. Even after every conservative correction, a residue remains. There are still more bright galaxies, earlier than the standard model comfortably predicts. The conventional explanations can bend the model far enough to survive, but only by stacking several adjustments on top of one another, each one plausible, none of them yet proven. And so, a small but serious group of scientists keeps asking a more dangerous question. What if the patches aren't enough? What if the reason the early universe looks too far along is that it really is because something about the universe itself, the way matter clumped, the nature of dark matter, the conditions at the very beginning, is not quite what we think? That is the radical road, and it leads to the deepest question this whole story raises. To walk down that radical road, we have to talk about the part of the universe we understand the least. And it is not a small part. It is most of it. Everything we have discussed so far, every star, every galaxy, every blazing red core is made of ordinary matter. The stuff of atoms, protons, neutrons, electrons. The same stuff you are made of. And here is the humbling truth. All of that ordinary matter, everything that shines, everything we can see or touch or build instruments to detect, makes up only about 1/6 of the matter in the universe. The other 5/6 is something else entirely, something that gives off no light at all. We call it dark matter, and after decades of searching, we still do not know what it is. We know it is there. Of that, we are certain. We can feel its gravity everywhere we look. Spin a galaxy, and its outer stars orbit far too fast to be held by the gravity of the visible matter alone. Something unseen must be gripping them. Look at a massive cluster of galaxies, and you see its gravity bending the light of more distant objects behind it, far more strongly than the visible matter could ever explain. And in the faint patterns of that ancient afterglow, the cosmic microwave background, the fingerprints of dark matter are written into the structure of the early universe itself. 5 separate, independent lines of evidence, all pointing the same way. There is far more matter out there than we can see, and it does not glow or absorb or reflect. It only pulls. Now recall the story of how galaxies are supposed to form, and notice the role this invisible matter plays. It is the foundation of everything. In the standard picture, dark matter clumped together first, drawn into vast invisible structures by its own gravity, long before any star existed. And only then did ordinary gas fall into those dark wells, pooling at their centers, igniting into stars and galaxies. The dark matter is the scaffolding. The galaxies are just the lights we hung on it, which means the entire timeline of cosmic construction, how fast galaxies could form, and when, is set not by the gas we can see, but by how quickly the dark matter we cannot see gathered itself together. And this is where the impossible galaxies become genuinely dangerous to our theories, because the standard model assumes a particular kind of dark matter, what physicists call cold dark matter. Cold, meaning it moves slowly. And slow-moving dark matter clumps in a very specific way, building up gradually from small structures to large ones, the bottom-up, unhurried assembly we have come back to again and again. That assumption is the beating heart of modern cosmology. It explains a staggering amount of what we see, but it also insists that the early universe should have been slow to build. That massive galaxies, that early, should not have had the time. So what if the assumption is wrong? What if dark matter is not quite as cold, not quite as simple as we have supposed? Physicists have explored the alternatives, and each one is a quiet revolution. Perhaps dark matter is warmer than we think, or interacts with itself in ways we have not accounted for. Perhaps the ripples in the early universe, the tiny density variations that dark matter gathered around, were stronger or differently shaped than the standard model predicts, letting structure form faster. Perhaps, in the most exotic ideas, the seeds of the first galaxies were not gas at all, but black holes born in the first instant of the Big Bang. Any one of these would let the cosmic scaffolding assemble faster and earlier, exactly as Webb seems to show. None of these ideas is proven. Most physicists still expect the more ordinary explanations, the bursting stars and the hidden black holes, to carry the day without rewriting the nature of matter itself. And they may well be right. But it is worth sitting with how little ground we are standing on here. We are trying to explain the timeline of the early universe using a substance that makes up most of the universe, and that we have never once identified. For decades, we have built exquisite experiments deep underground, shielded from all interference, waiting for a single particle of dark matter to reveal itself. And so far, nothing. The most abundant kind of matter in existence has never been caught. It remains the single largest unanswered question in all of physics. Imagine that for a moment. Most of the matter around you, threaded through your own body and the chair you are sitting in and the entire galaxy beyond, is a substance no one has ever seen, made of something no one can name. And now imagine that the impossible galaxies, glowing at the edge of time, might be a message about exactly that. The light we can see, arriving from the cosmic dawn, may be carrying news about the darkness we cannot. The thing that shines might finally be telling us something about the thing that doesn't. That is the radical possibility. That Webb has not simply caught our galaxy formation models making a mistake, but has stumbled onto a clue about the deepest unsolved problem in science. It is a thrilling thought. It might also be wrong, and the only honest way to tell the difference is building toward. Forget the galaxies for a moment, and forget the dark matter. Has the James Webb Space Telescope actually broken the Big Bang itself? Let's address the question directly, because the sensational version of this story, the one you'll see in dramatic headlines, says that Webb has broken the Big Bang, disproven it, overturned everything. So let's be clear and honest about what is actually at stake and what is not. The Big Bang Theory does not rest on the timeline of galaxy formation. It rests on several massive, independent pillars, and the early galaxies touch none of them. The first pillar is the expansion of the universe itself. Everywhere we look, distant galaxies are receding, their light stretched toward the red, in a precise pattern that says space has been expanding for billions of years. Webb's galaxies, with their enormous redshifts, don't contradict this. They confirm it. Their stretched light is the expansion, written across 13 billion years. The second pillar is that ancient flash we met at the very beginning. The cosmic microwave background, the afterglow of the hot, dense early universe, still washing over us from every direction. Its existence, its temperature, and the faint ripples within it match the predictions of the Big Bang model with extraordinary precision. Nothing Webb has seen disturbs it. The third pillar is chemistry. The theory predicts that in the first few minutes after the beginning, the universe forged a specific recipe of the lightest elements, about 3/4 hydrogen, 1/4 helium, and a trace of lithium. And when we measure the most pristine gas in the cosmos, that is exactly what we find. The early galaxies don't touch this either. So the Big Bang itself stands, firm on its pillars. What Webb has actually challenged is something more specific, and in its own way just as important. It has challenged our model of how structure grew inside that expanding universe. The story of how gas and dark matter gathered, how the first stars lit, how galaxies assembled and matured. That story, the timeline of cosmic construction, is what looks wrong. The universe didn't begin differently than we thought. It got organized faster than we thought. And that distinction matters enormously, because the rate of cosmic construction is woven into deep things. It depends on how much matter there is and how it's distributed. It depends, above all, on dark matter, the invisible scaffolding that everything else was supposed to gather onto. If galaxies grew faster and earlier than the models allow, it may be telling us something we don't yet understand about how that scaffolding behaved in the first hundreds of millions of years. A subtle revision there could ripple outward through our entire picture of the cosmos. This is why the field has split roughly into two camps. On one side are those who believe this is, in the end, a problem of astrophysics, the messy, complicated physics of stars and gas and dust. They expect that as the data sharpens and the models improve, the bursts and the top-heavy stars and the hidden black holes will add up to a full explanation, and the standard framework will absorb the surprise, bruised but intact. On the other side are those who suspect this is a genuine crack, a signal that one of our foundational assumptions about dark matter or the growth of cosmic structure or the conditions at the very beginning needs to change. They are not claiming to have the answer. They are claiming the question is real. And the honest truth is that we do not yet know which camp is right. That is not a failure. That is science, caught in the act in real time with the data still arriving. A theory met a telescope, and the telescope returned something the theory didn't predict. Now the long, careful work begins, of figuring out whether the theory bends or breaks. Webb has not handed us an answer. It has handed us a better question than we had before. And in science, a better question is how everything important begins. What is certain is this: the universe at its dawn was richer, brighter, and more developed than we ever imagined. Whatever the final explanation, we now know that the cosmic morning was not the slow, quiet, simple thing we pictured. It was already alive with light. The impossible dawn we have been exploring was only the first chapter of a much longer story. And it is worth following that story forward, all the way to us, Because the early galaxies are not some separate, alien prologue. They are our direct ancestors. There is an unbroken line that runs from that first light to the atoms reading these words. After the chaos of the cosmic dawn, the universe entered its most productive era. If the first few 100 million years were a frantic, surprising sunrise, what came next was high noon. Astronomers actually call it cosmic noon, and it arrived around 10 billion years ago, roughly 3 to 4 billion years after the Big Bang. This was the peak. Across the entire universe, stars were being born at the highest rate in all of cosmic history. Galaxies blazed with new suns. The cosmos was as fertile as it would ever be. And then, slowly, it began to wind down. This is one of the quieter, more sobering facts in all of astronomy. We live in the long afternoon of the universe. The peak of creation is behind us. Since cosmic noon, the rate of star formation has been steadily falling, and it continues to fall today. The gas that fuels new stars is gradually being used up and blown apart. Most of the stars that will ever exist in the entire history of the universe have, in fact, already been born. We are not living in the universe's morning. We are living in its slow decline, surrounded by the embers of a fire that burned brightest long ago. And our own story sits right inside that decline. Our sun is a latecomer. It formed about 4.5 billion years ago, well after cosmic noon, out of a cloud of gas that had already been enriched by generations upon generations of earlier stars. Think about what that means. The carbon in your cells, the oxygen in every breath you take, the iron in your blood, the calcium in your bones, none of it was made in the Big Bang. All of it was forged in the cores of stars that lived and died before the sun was born. We are, in the most literal sense, made of the ashes of dead stars. Stardust gathered into a world, gathered into living things, gathered at last into something that could look up and wonder where it came from. And this is why the impossible early galaxies matter so deeply, far beyond the technical puzzle they pose. They are the opening scene of the only story we are a part of. Those first furnaces, blazing in the cosmic dawn, forged the first heavy elements. Those elements seeded later stars. Those stars made still more elements, and still more stars in a chain that runs unbroken across 13 billion years and ends, for now, in you. When Webb stares at a galaxy at the edge of time, it is not looking at strangers. It is looking at the beginning of us. But the story does not stop with what Webb can see, because every answer the telescope has handed us has come wrapped in new questions. We still do not know exactly how the first galaxies grew so fast. We still have not caught a first star in the act. We still cannot see past the very edge of the reachable, into the deepest dark where the first structures were taking shape. To go further, we will need more than one eye on the cosmos. And the next generation of instruments is already being built. Webb opened a door, but it cannot do everything. And that is not a flaw. It is a matter of design. To understand why we need more telescopes, you have to understand what Webb gives up in exchange for its astonishing depth. Webb sees faint and far, but it sees through a narrow window. Its field of view is tiny, a keyhole onto the cosmos. It can study a small patch of sky in breathtaking detail, but it cannot survey vast stretches of the heavens quickly. So when it finds an impossible galaxy, there is always a haunting question. Is this a true representative of the early universe, or a rare freak that we happen to catch in our keyhole? To answer that, you do not need a deeper telescope. You need a wider one. You need to count thousands of early galaxies, not dozens, to know which surprises are common and which are flukes. That is exactly what the next great space telescope is built to do. The Nancy Grace Roman Space Telescope, expected to launch in the coming years, carries a mirror about the size of Hubble's, but with a field of view roughly 100 times larger. Where Webb peers through a keyhole, Roman will throw open a window. In a single image, it will capture sweeping fields of sky, finding enormous numbers of distant galaxies and rare cosmic objects. Roman and Webb are designed to work as partners. Roman will survey the heavens and find the strange, the distant, and the rare in huge numbers. Webb will then turn its powerful eye on the most interesting of them and study them in depth. One finds, the other examines. Together, they will turn the trickle of impossible galaxies into a proper census. And the future is not only in space. On the ground, in the high deserts of Chile and elsewhere, a new class of giant telescopes is rising, with mirrors far larger than anything we could ever launch. The largest of them will gather light with a mirror around 40 meters across, many times the size of Webb's. From the ground, peering up through the atmosphere, they face challenges a space telescope does not. But their sheer size will let them dissect the early galaxies in extraordinary detail, measuring their motions, their chemistry, and their structure in ways nothing before them could manage. There is even an effort to reach past the first stars entirely, into the dark ages themselves before any star had formed. That cold gas, the neutral hydrogen of the cosmic dark, gives off a faint whisper of radio waves, and a new generation of radio observatories is straining to detect that whisper, to map the universe in the era of total darkness, before the first light. If they succeed, we will have an image of the cosmos from a time when there was nothing in it to shine at all. So the frontier is still moving. The questions Webb raised, how did galaxies grow so fast? What were the first stars? What really lit the cosmic dawn? Are not the end of the road. They are the road, and the next eyes are already being built to follow it further, to push past redshift 14, to hunt the very first stars, to settle the great debate Webb began, and perhaps to raise new mysteries we cannot yet imagine. Because that is what has happened every single time we have built a more powerful eye. We expect to confirm what we already know. And instead, the universe shows us how much we still have to learn. Step back for a moment from the equations and the controversies, and consider what actually happened here. A species evolved on a small, wet planet, orbiting an ordinary star, in the outskirts of one galaxy among trillions. And that species got curious. It learned the rules of light and gravity. It built an eye out of gold and beryllium, folded it like paper, and flung it 1,000,000 miles into the cold and the dark. It pointed that eye at the emptiest patches of sky it could find, and it waited, gathering light that had been traveling since before the Earth, before the sun, before almost everything. We did this to confirm what we already believed. We expected the universe to nod back at us, to show us the quiet, simple beginning our theories described. Instead, it showed us galaxies that shouldn't exist, light where there should have been darkness, order where there should have been chaos. The universe looked back at us across 13 billion years and quietly told us we had gotten the beginning wrong. And maybe that is the most human moment in all of science. Not the triumph of being right, but the strange gift of being surprised, of building a machine to confirm your certainty and having it hand you a mystery instead. The impossible galaxies are not a defeat. They are an invitation. A reminder that the cosmos is always larger, stranger, and more inventive than our best ideas about it. The light is still arriving. Right now, photons from the cosmic dawn are landing on that golden mirror in the dark, carrying news from the first moments of creation, news we are still learning how to read. Somewhere out there, at a redshift we haven't reached yet, are galaxies even earlier, even stranger, waiting in the dark for us to look. We sent an eye to the beginning of time, and the beginning of time turned out to be more alive, more luminous, and more mysterious than anyone dared to imagine. The story of the universe's first light is not finished. We have only just begun to see it.